This slide is about the definition of domain set. Just like I have described to you in the previous video, a domain set is the set of all input values that make a function well-defined. So let's write that down again. Domain set is the set of all input values. So if you work with single variable functions, then you are going to have just one input. But if you work with multivariable functions, of course you are going to have multiple of those. Now back to this slide, set of all input values that make a function well-defined. A function well-defined. The keyword is right here, well-defined. By now, you should know that when a function is well-defined, it means that we can calculate or compute its value just fine. No problems with division by zero, no problems with square root of negative number or logarithm of negative or zero. Here we are going to take a look at the properties of points that are inside the domain set of both single and multivariable functions. Why don't we start with the single variable functions? So here I'm going to write about the domain of fx, domain of fx, which stands for the single variable functions. And of course, it's all about the input values here, domain set. So this is about the all possible values of x. All possible. And sometimes I like to use the word allowed. Values of x. Okay, the reason that I use the word allowed to, it means that we don't always have to rely on the equation to determine the range of x. Sometimes we can assign the range for the x by ourselves, like to limit its freedom, like what I'm going to do right here in this example. In this example, I am going to set a domain set for a certain function to be this. Domain set equal to the set of all x such that x is less than or equal to 3 and also greater than or equal to 0. And as you can see here, I just assigned this by myself, so this is arbitrary. Now the next thing I'm going to do with this domain set is to translate it into a graph. Since this domain set has only one variable, which means that the graph is going to have just one dimension, which is just x. Alright, this is let me fix the axis. Alright, so I have this x-axis and we have some important points right here at x equal to 0 and x equal to 3. And as you can see here, we are talking about all the x's that lies between 0 and 3. So it's going to be all about all these points in between. And do we need to include the endpoints 0 and 3? Of course, because we use the greater than or equal to and less than or equal to sign, right? As you can see here, we have this equal, which means that we have to include the endpoints. Alright, so sometimes we represent this kind of range to be this. The closed interval from 0 to 3. And once again, this kind of shape in the space, we call it interval in one dimension. Interval in one dimension, 1D. Now that you see the domain set being graphed in the space for the single variable function, why don't we try to do the same for the multivariable functions? So I'm going to do that on the right hand side. We are going to try to do the same for the domain set of function of x and y. Here I only stick with two variables because it's easier to draw on the graph. If I use z right here as well, it's going to be kind of hard to show it to you guys. Alright, so let's put the definition for this domain of f of x and y. It's going to be about the same. It's about the inputs, right? X and y. So here, all possible, or you can use the word allowed, values of x and y. Of course, we have two variables here, values of x and y. And just like I did before, I am going to make an example right here in order to graph. Example of this domain set, right? I'm going to set it to be this set of D such that we have all x and y as long as x is less than or equal to 2, greater than or equal to 0. Oh, maybe I'm going to use -1 to make it more interesting, right? -1. And of course, I have to include the conditions for the y variable as well. And y lies between 3 and 0. Once again, the numbers that I brought up here are arbitrary. I just made it up. You can choose it to be something else. You can choose x to be all real numbers. You can choose y to be on some other ranges. That's all up to you. But the point is, I bring this up just to graph it. So I'm going to translate this set into a graph. So let's take a look here. We have two variables, which means that we have the freedom in two axes. One on x-axis, like this, and another one on this y-axis. Now let's take a look at the ranges. X starts at -1 and ends at 2. So maybe around here, -1, and ends at 2, around here, -1 and 2. And we are going to include all these points in between. Alright, and of course, we are going to include the endpoints because we have the equal sign. Now, for y starts at 0 and ends at 3. Starts at 0 right here and ends at 3. 1, 2, 3 right here. Okay, and it's going to be all about these points. So as you can see here, we are working in 2 dimensions. And when we look at this range, when x is in between -1 and 2, it's not just going to be on this x-axis. We are going to have to include all these points as well, because all these points have x that lies between -1 and 2, right? And same for y between 0 and 3, not just on the y-axis, but everywhere here. Alright? So in the end, we end up with this rectangle that represents this domain set. Alright? All these points satisfy the conditions for this set. So when you see a shape like this, we usually call it region in 2D. Region in 2D. And it's going to be a little bit different from the interval in 1D. Alright, so we have one more dimension here. Now, the next thing we are going to do is to understand the properties of the points inside these intervals and regions. The first thing we are going to understand is the interior point. We are going to learn what it means by a point that is being interior. All right. The first thing I'm going to do here is to use the direct definition of interior. And as you know, interior means inside. So let's make a note right here. Interior means inside, like interior design. Design for the inside of your building, right? So let's write the simple definition down here for interior point. Interior point. Okay. For interior points, they stand for the points that are well inside the domain. Okay, make a note here, points that are well inside. This word is important. Well inside domain. What does it mean by being well inside? We can try to make this clear by looking at the graph. What about I pick some points and let's determine whether it's well inside. What about I pick one right here in the interval at x equal to 1. Right here at x equal to 1. It's quite obvious by the visual, right? By the look of this, that this point is well inside the interval. What about the region in 2D? If I pick this point at 0, 1, by the look of this is obviously well inside the region, right? Now, it's not so clear, right? What does it mean by well inside? What about we talk about the points that are not well inside? So I'm going to give you examples of points that are not well inside. For the interval, it's right here on the boundaries. This point not well inside because it's in between inside and outside. Same for the region. Points that are not well inside, between outside and inside, and we are talking about all these points on the boundaries. So in other words, interior points are points that are not on the boundaries. So let's make a quick note right here. Well inside means not on the boundaries. All right. Okay. Now, let's take a look at the next one, boundary points. Okay. We already talked about this when we brought up some examples of the points that are not interior points. So, for the boundary points, you can put this definition right here to make it clear. Boundary points are points that are on the edge of the domain. All right, points on the edge of the domains. Of domain. So the key word is right here, on the edge, and for interior points, well inside. It's kind of hard to understand this by using words, right? Even though we try to use the picture and try to explain it word by word, it's not so clear. Sometimes we can use the mathematical viewpoint to try to determine this property of something being interior and something being on the boundary. So let's take a look at how we use that kind of viewpoint to determine this property on the right hand side. So let's take a look at the one above. Here we are going to stick with this one, the first one right here. So let's try to listen to me on this. If you can create a surrounding ball around a point, all right, if you have a point and you try to create this surrounding ball, and in the end, if your surrounding ball has all the region inside the domain, if in the end your surrounding ball has all the region inside the domain, it means that that point is an interior point. All right? We use this surrounding ball to determine that, hey, this one is interior. Why? Because all the region of this ball is well inside the domain, all right? So what you see right here is surrounding ball right? Okay, so what about the boundary point? What's going to happen? So let's take a look here. If you have a point in the domain and you create a surrounding ball and it turns out that part of the surrounding ball is inside like this and another part of this ball is outside like that, if you see something like this, it automatically means that this point is on the boundary. If part of your surrounding ball is inside and the other part is outside, this means that this point is a boundary point. Of course, if you want to translate this into a theorem or a definition, it's going to be, we are going to use some inequalities to do this. But for now, we just stick with the idea, right? Now, the next thing I'm going to need to talk about is about a domain that is open, all right? Open domain and closed domain. So let's start with the easier one, closed domain. Closed domain means that this domain contains the boundaries, the boundary points. So the keyword is right here for closed. Domain is going to be the one that includes the boundary points. Right here. Include boundary points. So basically it means that this domain is going to consider all the edges, all the points on the edges. Like what we did up here, right? We include the edge, like 0. Like right here, 0, we include it. We include 3. So this one is closed. So what you see right here is closed domain. Same thing here. With the 2D, we include the boundaries like at -1 and 2 and 0 and 3. So we include all these boundary points. So what you see right here is a closed domain. This one also closed. Now, what about open domain? Well, it's going to be the opposite of that. It's going to be a domain that does not include the boundary points. All right, so let's make a note here. Doesn't include boundary points. How is that gonna work? Doesn't include the boundary points. Well, I'm going to make some adjustment to change the interval that we had before to be open. So the first thing, I'm going to erase this closed and erase this closed. If I want to get rid of the points on the boundaries, I can just change this sign. All right, this greater than and equal, greater than or equal and less than and equal to be something else. All right, it's gonna take a while. Give me some time. Here, I'm gonna try to change the closed domain into an open domain. So I'm gonna get rid of the equal. Now I only have less than and greater than. Less than and greater than. Less than and greater than. And there you go. You have this open domain. All right. And of course, when it comes to the symbol, you can change this hard parenthesis into a curvy one, and that can become this open domain. All right, we don't include the endpoints. All right, now what about the word bounded? This basically means that no x or y can go to -infinity or infinity. All right, so make a note here. No x or y can go to infinity or -infinity. It means that it's going to mean that it's bounded. Okay, now that we know the concept of this domain set, let's try to do some example. In these examples, we are going to try to describe the domain of some multivariable functions, and in the end, we are going to plot the domain set on the graph. So let's try to focus on the first one here. Here we have this function of xy, and it's equal to the fraction of xy divided by x squared minus y squared. Once again, I am going to use the same definition that we used before. Domain is all about the values of x and y, in this case, that makes the function well defined. And as you can see here, we have a fraction, and a fraction has a problem when it comes to the value when the denominator is equal to 0. So this is going to be a problem when this term is equal to 0, and we don't want that to happen. So let's translate that into a sentence right here. So this is about any x and y such that, oh come on, as long as take two. Take two. In these examples, we are going to try to describe the domain of some multivariable functions. And in the end, we are going to plot the domain set on the graph. So let's look at the first one here. Here we have a function of x and y, two variables, and that's equal to a fraction of xy divided by x squared minus y squared. And once again, in order to solve this, I am going to use the same definition that I mentioned several times before. Domain is all about the values of x and y in this case that makes the function well defined. And as you can see here, we have a fraction for this example, and a fraction has a problem when it comes to value when the denominator is equal to 0. So this is going to be a problem when it's equal to 0. So we do not want this to happen. Alright, so let's translate that into a sentence. We want any x and y, as long as denominator not equal to 0. Okay, so we are going to translate this denominator not equal to 0 into to include x and y, and that's going to be x squared minus y squared not equal to 0. We want this, alright, as long as denominator not equal to 0. So since we want this, let's work on this inequality, x squared plus minus y squared. We want this to happen not equal to 0. So here I can factor this inequality. So I have this x front minus back times front plus back not equal to 0. Alright? Now, since we want the whole term to be not equal to 0, it means that each of them cannot be 0. Because if one of them is 0, then the whole thing is 0. So this can be translated further that each one of them cannot be 0. So the first one is x minus y cannot be 0. That's the first term. Now the second term, x plus y cannot be 0. Both of them cannot be 0. And then we can work a little bit further. From here and here, in the end we have this y not equal to x, right? And this one, y not equal to minus x. And I am going to make a conclusion to these two conditions and make it a set. Alright, now in the end we have this domain set equal to the set of all x and y as long as or such that y not equal to x and y not equal to minus x. And we are going to try to plot this in two-dimensional space. So let's try to build this axis right here. Alright, this is x-axis and we have this y-axis. So why don't we start with the first condition, y not equal to x. I'm going to start with y equal to x. If I want to plot y equal to x, it's going to become this line, right? Y equal to x. And if I plot this, y equal to minus x, it's going to be this line, y equal to minus x. But here we want the not equal to, right? We focus on this not equal to. So in the end, it's going to be anything as long as it's not on these two lines. Okay, so let's erase these two lines. We do not want these lines. We want anything outside these two lines. So it's going to be this. Okay, dotted lines. We don't want them. Alright, that's for the y equal to x, and this one is for y not equal to minus x. So in the end, the region for this domain set is going to be any point outside these two lines. Any points out here. But anything on the lines, not good. Alright. So this is how it looks like in the space for this example. Now let's move to the next example, and with this one is quite complex. And as you can see here, we have this lots of things going on. We have ln, we have square root, we have fraction, we have three things going on here. And as we know, when it comes to ln, let's take a look at the first one. Ln is well defined when the inside of ln is greater than 0. Ln 0 is not defined, ln of negative number is not defined, so we want y minus x to be greater than or equal, greater than 0. Y minus x to be greater than 0. You can make a note right here is that this is about inside of ln must be greater than 0. Must be greater than 0. And that's how I get this inequality, the first one. Now the next one, the inside of the square root has to be greater than or equal to 0. So we are going to focus on the inside of the square root right here. the inside here has to be greater than or equal to 0. We do not want any square root of a negative number. So the next condition we have right here is x minus y plus 2 greater than or equal to 0. And let's make a note here that this is about the inside of square root greater than, well, I can say non-negative. That's better. Non-negative. Alright, that is the second condition. Now the next thing is about the fraction. You can see that we have a fraction too, so the whole fraction cannot be 0. Just like in the first example, the whole fraction, the whole denominator cannot be 0. Right? This is going to be a problem. So we are going to focus on the denominator, which is this. The square root of x minus y plus 2 not equal to 0. Right? So this is about denom not equal to 0. And we can work a little bit further with this third condition. So we can get rid of this square root. It's the same thing, right? As long as the inside is not equal to 0, then the square root of that is not equal to 0. And then we can combine these two. Combine these two. This term, in the second condition, it has to be greater than or equal to 0. But then for this one, it requires this term to be not equal to 0. So in the end, you can combine them into one condition, which is x minus y plus 2 greater than 0. This equal is eliminated. So in the end, we have this instead. All right? For the second condition and third conditions combined. Now we have this one as well. So let's work on these two. So here we have, what do we have here? We have y greater than x. Okay? Now what about the next one? We have y, I'm going to work with this one, right? Move y to the other side, y less than x plus 2. So in the end, we have these two conditions, and we can set the definition for the domain set to be the domain set equal to any xy as long as or such that y has to be greater than x, but in the same time and y has to be less than x plus 2. Alright. The tricky part is this combining of second condition and third condition, but in the end we are going to end up with just one inequality. And then right now I am going to try to plot this in 2D space. So we have this, right, x-axis and y-axis. So I'm going to start with this this first inequality, that is y greater than x. I'm going to start with the equation first. Y equal to x is going to be this line, right? Y equal to x, and this condition require y to be greater than x, so it can be anything up here, right? And since we have this y greater than x, it means that we do not include the line itself. So let's erase the line and make it dotted. We do not include points on the line because y has to be greater than x. So make a note right here, y has to be greater than x. Now let's take a look at next one. Y has to be less than x plus 2. So the first thing I'm going to do here is to plot y equal to x plus 2. Y equal to x plus 2. What is it going to look like on the graph? So it's going to be a straight line again, and it's going to intercept the y-axis at 2, maybe around here. So it's going to be this line, okay? Now, this condition that we look at requires y to be less than x plus 2, so it has to be anything that is less than this line. And once again, we have this less than sign, so we do not include the points on the line. Alright, so I'm going to change this to dotted red line passes through this y equal to 2, right? Right here is 2. Okay, and now we have to find the overlap regions between these two colors of green and red. So in the end, it's going to come out to be this dotted line, and we want all the y that is less than this region. Alright, and then we also have this dotted line at y equal to x, and y has to be above this line. So we are talking about this region between these two lines, and that is the shape of this domain in the 2D space.